Yeah.
All right, good morning, guys. So let me talk about this week here. We're going to focus on some of the free response topics that are common on the AP exam, and we're going to create a test out of it. So initially I had it being Wednesday, but I want to give us a little more time to kind of let these practice problems sink in. But I don't want to lose any instruction days. So I figured that we'll move it to Friday, but we'll start our next unit Wednesday and Thursday. And then obviously that's not going to be on the test, that's the next unit, but it allows us to go through the material and then still have the second half of class to do more review for these FRQs. Okay. You do need your calculator. Whether you have a 36 Pro or T.4, 83 or 84, those are sufficient. Now, if you're using one of the older calculators that don't have math prints, I'll go over those steps with you. It doesn't look as clean, but it can do all the same things that the calculus can do. It just doesn't have the nice math prints matching up. So okay, so the three FRQs that we're going to see in your packets, you have particle motion, you have Riemann sums, and you have derivative graphs. So we'll just cycle through the three different types and get practice with them. Typically, students do better on this portion than on the first portion. So just to kind of give you, that's because once we get into the rhythm of these problems, they all kind of follow the same thing. So we just have to get comfortable with them. Okay. Any questions about this week? Okay. So I want to start off by so if you can have your calculators out. I'm going to start off by going through what the calculator can do for us. Okay. So I want to kind of walk through the process so that we know how this looks like from a manual perspective versus what it looks like from a calculator perspective. So for instance, if I gave you 3x squared plus 2x, what's the derivative? 6x plus 2. Okay. If I ask you what is f prime of 1, you would say 6 times 1 plus 2, which is 8. So this is evaluating the derivative at a point. Visually, what this is doing is to find the derivative, you want to figure out what the exact steepness of this graph is. It'll give you that exact value. So the calculator can do this for us. It can take us from the function down to the derivative at a point. The calculator is not going to be able to give you a derivative function, but it can evaluate the derivative for you. Okay. So depending on which calculator you're using, I'm going to put both up, and then we'll just practice entering both in and seeing if this makes sense. Okay, so first off, 3x squared plus 2x. So if you, I'll do the graphing calculator first. You're going to go to math. And then option 8, math 8, and deriv. And a lot of this I put on page 18 and 19, or rather page 19 through 20 in your packet. Okay. So n deriv, hit enter. So you see that notation, which is asking, you want to tell the calculator to find the derivative out of a function at a point. So d over dx indicates that you want to find the derivative. So go ahead and enter x in that denominator space, d over dx. And you want to enter in the function that you're working with. So 3x squared plus 2. Now we're always using the variable x in your calculator. Even if on paper it may be y or theta or t, don't ever try to match those variables. You're always using x. Okay? If you try to match the variable on your problem, if it's a different variable, it's going to throw the calculator off. So just always use x. Okay? So I want to find the derivative at 1. So enter 1. Oh, I'm sorry, I messed up. 3x squared plus 2x. That's why it wasn't matching up. Oh, by the way, if you want to, yeah, so if you want to insert something and do second insert, and it'll allow you to, but in this case, sometimes calculator allows you to. There we go. So the calculator allows you to find the derivative at a point. Same thing here on the 36 Pro. There's that d over dx. Do you see that natural under above natural log in blue? So if we do second d over dx, same notation, except it fills in that dx for you. So same idea, plug in the function 3x squared plus 2x. Again, you're always using x. Don't try to, I know there's other variables here, but just always use x. 3x squared plus 2x. Okay. Again, the calculator can't find the derivative function for you, but it can evaluate the derivative at a point for you. So just like how we were able to do on paper. So you can imagine that we can do this for much more complicated problems that we don't want to, that is meant for the calculator. So on the AP exam, sometimes they expect you to be able to evaluate the derivative at a point, and so that you can move forward with what they're really trying to get you to work on. And okay, so you will never see a problem like this on the calculator portion where they're just asking you to find the derivative at a point. It's usually using this information to move forward with the rest of the problem. Okay. Any questions with the steps? Okay, so that's one big feature that we're going to be using over the course of every time we do a calculator work, we're going to be using this feature. The second feature is that calculator can also evaluate a definite integral for you. Okay, so let's work it out by hand just to see what this looks like. So this we can go through power rule, right? 3x squared plus 2x, 3x squared becomes 3x cubed over 3 plus 2x squared over 2 plus, well, yeah, plus c drops out because of the integrals, but we can go ahead and do some reducing here. So x cubed plus x squared. Okay, now that we found the antiderivative, we're ready to evaluate our bounds. Okay, upper bound first. 2 cubed plus 2 squared. Then what? Minus big parentheses. 1 cubed plus 1 squared. So we have 8 plus 4 minus 1 minus 1, which is minus 2. 8 minus 6 equals 2. Sorry, 8 plus 4 is 12. 12 minus 2 is 10. So I want to show you that the calculator can help us get from here directly to here. Okay. So it's also under the same menu in your graphing calculator. You're going to, instead of go to math 8, which is n deriv, you're going to go to math 9, which is fn integral. So one is for derivative, one is for definite integrals. Choose math 9 option. And then you see this nice math print notation where you're just going to match up exactly as what you see there, right? Your lower bound is 1, your upper bound is 2, your expression integrand is 3x squared plus 2x, and then you got to make sure you fill in with the dx at the end. Okay, we should get the same answer that we did by hand. Similar on the TI-36, if you look at there's a definite integral notation right below d over dx. So do second definite integral. Same idea, enter in. Okay, any questions? All right, so those are the two big features that we're going to be using on the calculator for the test. Really, these are really the main big ones that we'll be using. There's other features, such as the graphing feature. I think we'll get to that a little bit later. Yeah, but right now I just want to focus on these. There's a bit of a, I want to say shortcut, but especially if the function gets messier and messier. This is on page 19. What we can do is, rather than entering everything into this home screen, you can have this saved in a different location, and that way you don't have to call a really messy function all at once. So I like to use it, but it's up to you whether you like this feature or not. This is where, let's say I wanted to store a messy expression inside a different variable. So I'm going to go to vars, yvars, function 1 and y1, and let y1 hold that messier expression. So I'm not going to do a messy one right now, but just want to show you how that works. So if you go to y equals, I'm going to type in the same function that I've been working with, 3x squared plus 2x. You can also do this on the 36 Pro, but it doesn't feel as useful because it can't hold more than one function. So okay. So once you have that entered in under y1, which is at the top of the screen, then go back to your home screen. Like go back if you do second mode, it'll take you back to your home screen. And now we're just going to go through these steps here. So we're going to go to vars, yvars, function 1y. So if we go to page 19, it's on that half page. So vars, variable, which is here. Scroll over to yvars, y variable, function y1. So now it's holding, it's holding that function now. So let's say I wanted to do the same notation here. So if I do math 9 from 1 to 2, rather than typing in this case, is not a big deal. 3x squared plus 2x is not hard to enter, but imagine a really messy function that you would rather just, if you're calling it over and over again, you don't want to keep typing in the same thing over and over again. So I can go to vars, yvars, function y1, and so it inserts that expression into that space, and then we get the same thing. So it's up to you if you want to use it. It's good for later when we're having to hold multiple functions and calling multiple functions into the same definite integral problem. So it's here, vars, yvars, function y1. Okay, so let's look at page 1. Okay, a particle moves along the y-axis. This is a particle motion problem. I'll go ahead and particle moves along the y-axis. So imagine a particle is sitting on the y-axis, and it's only got 3 things that it can do. It can go up, it can go down, it could stay motionless. Right? So going up would indicate that your velocity is positive, and going down would indicate that your velocity is displaying a negative behavior. Right? So if we get positive value out of velocity, we know it's moving up. If we get a negative velocity value, we know it's in that moment in time it's going down. Okay, particle moves along the y-axis. In which direction is the particle moving at time t equals 1.5? So I can directly just find v of 1.5, plug it in, get the value, and interpret, right? Positive means moving up, negative means moving down. So make sure that you are in radian mode. Anytime you're dealing with trig, you always want to be in radian mode. In fact, on the AP exam, you should always be in radian mode, never in degree mode. So if you go to mode, make sure you highlight radians. Okay, so we're just going to plug this in, right? Because we know that v of 1.5. So no derivative, no integrals involved here. We just are directly inserting into the velocity function. So obviously you can just enter this as I just see it, but if it's on my 36 my graphing calculator, I like to just take advantage of the fact that if I just enter the function in once, I can just keep calling it, whether it's for derivative or evaluating or integral. So I'm going to type this in t sine t squared. But again, we want to always use x, right? Never use any variable except x. X sine x squared. Okay, again, second mode will take you to your home screen. And now I'm just going to call the function vars, y vars, function y1. And I'm just going to insert 1.5 directly into the function. And that way I don't have to go and replace everything manually. It'll just do it for me. I get 1.167. Okay, on this, I would just go ahead and enter in as you see it. It's not worth the effort to create a function and plug in. But I think this one we can use over again. It's nice. All right, so what does that tell us? Moving up, right? Our velocity is greater than 0. Positive velocity means particle moving up. And we'll specify at t equals 1.5. Okay, part B, find the acceleration of the particle at time t equals 1.5. What's the relationship to get to acceleration? Just the what? The derivative, right? So basically, if I do v prime of 1.5, isn't that the same thing as a of 1.5? So we can use our derivative feature, right? So we can use our derivative feature, n-deriv. We can make the calculator find the derivative for us at a point, or evaluate the derivative at a point for us. So math 8. And then on the 36 Pro, it's that blue notation there, d over dx. So you're going to type in the original function, or in this case, our original velocity function, and then plug 1.5 in. So here, d over dx. Again, I already have my velocity stored in y1. You can keep entering in x sine x squared if you like, but if I know I'm going to be using the same function over and over again, it's a little bit faster to just have it stored. Okay, so ASCII, so I know y1 is my velocity. This is going to push it into the acceleration function level, and I'm going to evaluate the derivative, the acceleration at 1.5. Okay, so V prime of 1.5 is negative 2.049. So is the velocity increasing or decreasing? Yeah. So we talked about how velocity increasing, decreasing is just another way of saying is acceleration positive or negative. So A of 1.5 is negative 2.049, which is less than 0. So velocity is decreasing. At t equals 1.5. If you're having trouble with your calculator, I want to probably end about like with 5 minutes left and just walk around real quick to see if I can answer any questions you have with your calculator. Just hold on tight. So the part C says, given that y of t is the position of the particle and that y of 0 equals 3, find y of 2. So this goes back to this formula that I shared when we were doing some particle motion problem. And this is on page 21 in your packet. There are all these variations of first theorem that we want to be familiar with, but they're all based off the same thing. They're just saying that a definite integral of a function is the antiderivative of b minus antiderivative of a. So I want to, this is one rearrangement that is very useful for us, is the idea that if I'm looking for any final position, I can always think of it as, okay, whatever the given position is, I'm going to take that and add it to my displacement. So wherever I start off at and however much movement I make in that interval is going to take me to my destination at a point in time. So if I adapt this into this problem, I can say, well, y of b is equal to y of a plus the definite integral from a to b of v of t. So if I know a starting point that the problem gives me, and if I know how much movement I make in that time interval, I can figure out where I'm going to end up. So in this case, I want to find y of 2. So I want to figure out, where is this particle going to be at 2 seconds? Well, I know that it's going to start off at 3, and I'll replace that with 3 in a moment. And that I figure out how much movement it makes in this time interval. Okay, so we'll make the calculator do this portion for us, and then we can plug it back in and add it to 3. Okay, so math 9. Definite integral from 1 to 2. You can type in x sine x squared, but again, I like to just call the same function over and over again, and not have to type in as much. Okay, definite integral button on the 36 Pro. So we know that between 1 and 2 seconds, it's going to move 0.59 units up. So how can I find out where he's going to be 2 seconds in? Add this to what? To 3, right? Y of 0 is 3. So he's already starting 3 units up, and he's going to move 0.59 on top of that. Oh wait. Got it. Whoops, sorry. From 0 to 3. Sorry, 0 to. Oh, I sorry. You're right. My bad. I typed in from 1 to 2, but I should have done from 0 to 2. There we go. 0.826. My bad. I'm gonna round up, but you can do anything with that third, as long as you round it. Yeah, so calculator, AP exam wants you to round to 3 decimal places. So you can do anything with that third decimal place. You can either just truncate it and then just take whatever that third one is, or you can use that fourth one to either round that one up or keep it. So you have some flexibility when you round it 3 decimal places. Yeah, you can either, go different interpretations, and so either one is fine. All right, any questions with this? Now, total distance. There's a unique formula for total distance. Total distance, because this is displacement plus initial equals final position. Total distance is just the depth integral from A to B, absolute value of V of t. So let me show you how to arrive at that in your calculator. Again, you're going to go to Math 9. We're going to go from 0 to 2. Okay. Let me get to the same point on this calculator. Okay, so you have to find your absolute value button. So if you go to Math, Number, you see that top option there, ABS. ABS is absolute value. So again, Math, Number, it's in the same location. And so you're just going to insert your velocity function within those absolute value bars. So here I'm going to call it under bars, y bars, 1. And then here I got to type in x sine x squared. Okay, it may take a moment. So total distance traveled is 1.173 units. And it finally came up on the 36 Pro. Any questions here? Now, let me make a distinction here because it gets kind of confusing. Well, because they're all kind of similar. So displacement is just the depth integral from A to B of V of t. Okay. Final position requires you to have a starting location. Then I got to tack on the displacement. Okay. But total distance is just depth integral from A to B of absolute value of V of t dt. Okay, total distance is not this. See a lot of students do this on the test, so that's why I want to bring this up. Sometimes students get confused with final position versus total distance, and they want to add that to the initial position. But total distance doesn't care where you start. It just wants to know how much movement you've made between A and B. So that's not total distance. Okay. So I'm sharing that in the hopes that you understand that distinction. Displacement is just how much net gain you made between 2 endpoints, between 2 intervals. Final position is actually tracking where is the object at that moment in time. So I got to know how much it travels, and I got to know where it starts at. Total distance is just keeping track of how many, in the quote unquote, steps you're taking, right? If you're going forwards and backwards, it's counting everything as positive. And I just want to know how many steps I took. I don't care where I end up. Okay. Are we clear with those distinctions? Okay, so keep those in mind because I see students mix things up or combine things, concepts that's not supposed to be combined. Okay. Right, we'll circle back to particle motion, but this is the big idea here. Knowing how to go between velocity to acceleration to position, back and forth. Okay. All right. Number 2. This is a Riemann sums problem. Okay, so the temperature in degrees Celsius of the water in the pond is in a differentiable function, W. The table above shows the water temperature recorded every 3 days over a 15-day period. Use the data from the table to find an approximation for W prime of 12. So if W of T is the temperature at a specific day, what do you think W prime tells us? Right? What's another word for derivative? Slope, okay. What's another word for slope? Yeah, rate of change. Okay. So, but what we don't want to say is we don't want to say velocity. Okay, I think that's typically what students think of when they're given a word problem. They think that first word is velocity. So we don't want to say that word velocity if it's in a different context. Okay, so you want to say either rate of change or, but usually it's going to be like word of. So this is rate of change of what? Temperature on the 12th day. Yeah, the rate of change of the temperature 12th day. Now we don't have a function right now to find the derivative, but what can we do? We can find the what? Slope. Yes. So slope is not going to be perfectly accurate, but it's okay because they're asking us for approximation. They're not expecting exact value because we're not going to be able to know that based off the data. So slope involves what? So what can we use to find slope? Yeah. So I need how many order pairs? 2. Okay. Which one would you choose? So just to let you know, you have a couple options in front of you. Basically, if you use any order pair near 12, that's good enough, right? So in this case, if you use these 2 order pairs, you can make an argument for that. If you use these 2 order pairs, you can also make an argument for that. You can even make an argument for between 924 and 1521. That's also acceptable. So basically, any order pairs involving around 12 is good. But if you're using anything too far away, then that's not as accurate, right? So yes. Yes. So yeah, I think these 2 are better options, but AP exam also allows you to use points around it. But yeah. But yeah, I like my first instinct is I want to just use anything involving order pairs, but I'm just letting you know. College board also you can also make an argument between 9 and 15. But okay, so we want to find, I can say I'll use the last 2 here, but you don't have to. So change in temperature over the change in time. So 21 minus 22 over 15 minus 12. Okay. So what does that tell us? What's the unit of measure, do you think? What's happening on the 12th day? Approximately. Temperature is decreasing by 1/3 degree per day, Celsius per day. Yeah. Okay, so part B, approximate the average temperature. So we have a formula for this. Average temperature. What did we just learn? Average what? Remember average value? Right? We just saw that on the test, right? Average value is 1 over b minus a, integral from a to b of f of x, but I can say w of t. Right? Between 0 and 15. So I'm going to accumulate all the temperatures and then find the average amongst all those temperatures that I have. So what word do we associate with this notation? Area, yeah. And what are we going to use to approximate area? Trapezoids, yep. So it's telling you how to go about figuring this out. Okay, so we're going to add up a bunch of trapezoids. So 1/2 width, height 1 plus height 2. Now, what's nice about the width? It's all the same. So if it's all the same, we can do that little bit of a shortcut that we talked about, trapezoid approximation, where I can factor out the width, and then I can just add up all the heights. And what do you know about all the heights? What's the pattern with the heights? All the middle ones are what? Used twice, except the ones at the end. Yeah. So 1/2 width. I'm going to add up all the heights, and then just double all the ones in between. Another option is I can just do 5 trapezoids with each of them separate, but this is a little bit faster. Okay, I'll save some time here, but the average temperature, we don't want to forget about that width component, right? So it's 1/15 of 3/2. Well, 3/2 times all that mess is going to be 376.5. Now, whenever you're dealing with a word problem, you always want to kind of go back and see, wait, does this number make sense? Because if you didn't go through, let's say you forgot to divide by 15, and you're looking at 376.5, and you're looking at the temperatures here, that doesn't feel like an average temperature, right? If your temperature is only ranging between 20 and 31, it should never reach as high as 376, right? So if you forget to just divide by 15 and you're looking at that number, you know something's missing. It should make sense, right? 25 degrees, that feels reasonable looking at these numbers if you're ranging from 20 to 31, right? Okay, any questions so far? So now part C and D, we're going to revisit the concept from A and B, but A and B, we're doing approximation, but C and D, you're actually given the function, so you can actually use the calculator to, find the exact rate of change, use the calculator to find the exact area. Okay, so we're going to go to our calculator, revisit the concepts from A and B, but from a more accurate standpoint. Okay, so there's your function. A student proposes that a function P as a model of the temperature of the water in the pond at time T, where T is measured in days, and P of T is measured in degrees Celsius. Find P prime of 12. So we're going to look for the same thing. We're just using a different model. So, and potentially more accurate. So we want to find the rate at which temperature is changing on the 12th day, which, at first we're given the table of values, but now we're given the function that we can use. So in your calculator, P prime of 12. So I'm going to find the derivative. Yeah. So derivative. I'm going to enter it under y1. Again, we always use what variable in the calculator. Always use x, right? Even if they're giving you a different variable on paper, you're always using x. So 20 plus 10x. E is under natural log ln. Do you see that? So second ln will take you to that exponential. And then e raised to the, 10x e to the negative x over 3. Now, if you're using a negative notation, make sure you're using it correctly. It's below 3. It's print that negative inside the parentheses there. Okay, I'm going back to my home screen here. Math 8 will get me to my n deriv. I'm going to call my function vars y vars function y1. Sorry. And I want to find what is the rate of change on the 12th day. E is in that first column there. See that e raised to the negative x over 3. Specify the location. You want to figure out the rate of change on the 12th day. Okay, so what does this number tell us? That on the 12th day, what's happening? Temperature is decreasing at around half a degree Celsius per day. Part D, same formula as part B, but instead of using trapezoids, we have a function, we have P of T that we can insert and make the calculator do all the work for us. So 1 over b minus a, integral from a to b of P of T dt. And then my a and b is just 0 and 15. Math 9. I already have P of T stored under my y1. Right, this is not the average temperature, right? I still got to do well with it. Yeah, multiply by 1/15 or divide by 15. All right, that's reasonable. 25.75 degrees Celsius. Okay. Any questions? Let me just spend a few minutes on the notation for number 2. I just want to talk about this for a moment and we'll get into it a lot deeper here. So let me spend a minute here. Let's say g of x is the integral from -3 to x of f of t dt. Okay. Let's say that's a starting function. It looks messy, right? But it just means my g of x is just the area under my f of t. If I want to find g prime of x, what's going to happen to this notation? Right now, this is sitting one level above f of t. So if I find the derivative, what's going to happen to this level here? It's going to drop down to what? Just f of t. Right. So the integral just tells us that it's sitting right now, it's sitting one level above it. And if I find the derivative, it's just going to come back down to the f of x level. Again, this is second theorem. A derivative of an integral just wipes each other out. And if I want to find the derivative, it's going to bring me down to f of x. Which means that if I want to find g double prime, what's going to become of f? F prime, yep. So this is the big idea that we're going to explore with these. So if you understand this concept, you're either using a graph to find the area, you're either using the graph to find an ordered pair, or using the graph to find the slope. And we're going to explore that relationship tomorrow. But these are the 3 FRQs that we're just going to practice through. We'll spend a full day tomorrow, half a day Wednesday, half day Thursday, and then test Friday. I will come out with the schedule for help sessions, but I think we're at a good spot. Okay, you don't forget your phones.